Okay, so you heard from Ajith about kind of the background of these detections that LIGO has made. Now I'll kind of give you a reminder of what they are very quickly, and then talk about kind of what we ought to learn the systems in a bit more detail than you heard from Ajith, and also about testing and some bit of astrophysics. So here's just a reminder that we have this first one, which is much more pleasant one. This second thing that is not necessarily a black hole, but it's likely more astrophysical than just noise. And finally, this we just announced recently. So this is actually a summary of what I'm calling the OMPH paper. Was by a black hole writer's paper that actually kind of describes everything and also describes this event. So here's kind of the other half of this is hardly barely alias. I hope this won't be a problem for other ones. So here these are showing you these signals per time domain, showing you do you have these high mass signals down these low mass signals which last much longer in the band. Of course, they all are going on for much longer than we're able to see them, but we have this cutoff around 40 hertz. Or here it's just showing you what you see in the detection part with 30 hertz. The parameter restoration go about 10 hertz lower. That you only see a few cycles here. So this one you see is quite high up in the frequency domain, going above noise curve, and then the next one and here, and then the lowest one is the one that we're not quite as well. Note that, of course, here I'm giving the masses that actually control. You see in the detector, there's a 10 to 20% larger, depending on the distance from the actual physical masses of the source to the redshift. And of course, the nice curves because they are ones that have been given by the parameter estimation. Again, just a reminder, this is one you should not trust so much. So here now is going from the detection to actually the parameters. So here we have kind of 4 plots giving you, 3 plots giving you pairs, 1 plot giving you the distance, and it's a zero distribution. So these are just these 80 to 90% credible intervals here for these small mass and larger mass, so the secondary primary masses. So here, showing you again, these are these curves about constant chirp mass that he's talking about, these 2 low mass events. For the first one, we see it's rather more well constrained because you also see the ring down. Then also comparing the final mass and final spin, you see that they're all about the same final spin. This one is a bit higher. When I'll explain a bit. This is just because you're mostly seeing the effect of the orbital angular momentum basically. Basically seeing the effect of the orbital angular momentum you have right before finding mergers, and not so much an effect of each of the individual spins by them. Obviously, the final mass differs by a bit more. It is directly correlated with the total mass. These things all radiate about the same 3 to 5% of the total mass, which is, of course, an enormous amount of energy. Here also showing you the mass ratio, which you see is not well constrained at all, as you can see here. And also, this is the dominant effect of spins on the orbit is effective spins, and this doesn't involve the aligned components spins. And the simple scalar quantity there. So here you see that for these 2 events, the effective spin was 0. They could have been quite highly spinning, possibly spins in the plane, or just things with one spin up, one spin down, but we had no way of knowing this from the data. Here, the effective spin is highly constrained to be away from 0 at 9% time. So if we can say, as I'll talk about later, that one of these holes we know is spinning not very rapidly, could have been spinning rapidly, we know it has been spinning. No, sorry, this is the effective spins, which is basically a sum of the aligned spin appropriately weighted by the masses. So this knows something about the in-plane spin. So you could have very high in-plane spins, so 0 effective spin. You also have, say, 1 spin up canceled by 1 spin down, so 0 effective spin. So basically, it's the leading order spin orbit coupling you get. The high order terms, which actually contain the other densities, they're just not measured as well. And as you were saying, both of these are about the same distance, and the one that we didn't see So clearly was more likely further away. So kind of constantly again, here are now the total masses. Here the source frame without the redshift, the small one that I quoted earlier, up at a factor of 3 between the two. So we're starting to actually see the diversity of the black hole in the universe. And they also have the same factor of 3 in radiated energy. You'll know that this is rather more well constrained than the total mass. And sometimes this is because this is what you see in the waveform itself. However, even though the radiated energy is by a factor of 3, the peak pressure wave velocity, that's how what is the maximum rate at which this energy is radiated, is actually very close to the same and quite impressively high for all three. That's about 200 solar mass c squared per second. So the reason why it's dependent on mass is, again, it's a dimensionless quantity. So it's energy by time in g equals 1 units. This is dimensionless, so it has no difference with mass. But it's not very well localized in the sky. Oh, it's very hard to see. It's bad. So here's a plot in celestial coordinates and then also in Earth-based coordinates. You see that the lattice signal was the most well localized you expect. It's still around 230 square degrees, so it's a pain to electromagnetic responders follow up. They did an absolutely amazing job looking for something, just in case there's anything there, even though you don't expect anything for a black hole. And also the two data sources, you see these are basically on a curves which are constant arrival time for the two detectors. So here they're shown on the Earth, here are the two detectors, because it's the maximum times arrival is the other one. So as we get more detectors, as you said, as the vehicle detector comes online, we hope to, at least for the latter part of O2, will be there, and then that's, of course, Cargo and Windio. We also start getting much better sky localization to actually be able to triangulate better. So here are a few special properties of the latest that we announced a few days ago. So it's probably the lowest class binary detected so far. And it's basically the only binary of the three that we can say actually had synchron. The other two are consistent with actually the very simplest case of a non-spinning in binary. In fact, the case is like the first test case always do with the numerical digit code, say non-spinning in equal mass binary is actually quite well consistent with the data. It's not the very best fit, but it's very well consistent. But in this case, you actually needed some spins, so at least one of them had to be spinning at least 20% of the maximum, actually, maybe at 99% critical level. So it's actually quite a strong statement. And this corresponds to about 10th of C for horizon velocity. For comparison, maximum spinning in C, the horizon velocity rises extremely rapidly with the spins. You actually have to get up to even close to 0.999 before it's close to C. This also has the lighter median parallel span, about 74% maximum compared to 36% maximum the other two. So here's a plot showing you actually our best estimates of the individual spins of GBO2 parallel span. So this shows you primary spin, secondary spin, magnitude is shown here, and then the orientation with respect to the normal to orbit, basically Newtonian home-dynamic momentum, is shown in this angle. So you see the secondary spin is very poorly constrained. The primary spin is mostly constrained within 0, but it's not. You see there's still some blue shading all the way to 0. So there's some probably there's this one was more, but it's more likely it's this one. And so also it's more likely it's consistent with being aligned, but it's more likely that it had some tilt. But unfortunately, we can't say that there was definitely processing that it's tilt and sort of spin in the order plane process with any confidence. We hope that as we get more binaries and signal resolution, we'll be able to say definitely that some binary actually had this interesting procession effect. So here's a visualization, just an aligned spin case with one spin up on the more level, the other spin down. Mass ratio of 3.3, still consistent with the data, though a bit off to one side of the area. This is showing you actually to set up just the chart, not just the waveform, showing you how long it was. We had about 55 cycles in band, and that's for about a second. But also showing you the wide range of frequencies with its sweeps, compared to order of magnitude, and some sort of rough indication of the velocity of the system from the frequency. You see it gets to about over half speed of light. So here you see this is the parent horizon of one mass black hole and the rest of the black hole. They just spiral out, they gradually spiral in towards each other, and then at the end you'll see they get back, and that's where this frequency is being able to also increases, and then finally they'll merge. We find the planet hole, and then we'll finally get to see more interesting physical collision. We play this, and you see the shading here showing you the deformation of the horizon by its intrinsic Ritchie scalar. Thanks to this really interesting space-time collaboration for this light visualization. So now to move on from parameter estimation to test of general relativity. For the first signal, there was an entire paper written about tested. She also just goes through these quite rapidly. So there was a relatively high star and high mass. You saw the motion ring down into some of the end spiral. I'd be able to do a whole bunch of tests. So first was you just take the most probable waveform and subtract it from data. Do you get residuals that are consistent with noise? For instance, if you look before or after, or is indeed you find this, that here are the actual things with signal to noise, these are building signal to eclipse probability, and these you see that after you subtract them are well consistent with the data you see elsewhere. You also this the low and high frequency parts of the signals. You see this is the final Latin spin. You just look at the low frequency part of the signal. The final Latin spin, you just look at the high frequency part of the signal. And then, of course, the smallest one is if you look at the entire signal, they all work with each other. So this is a kind of a test that indeed is matching well with the waveforms. Again, you could also say, well, if you had a theory with a massive graviton, say something else where you have dispersion, where different frequencies of actual wave travel to speeds, you actually see this as some sort of deformation of the signal you expect. You actually put constraints to apply this on the constant wavelength of the graviton. They're quite neat. Comparative with some other constraints, actually do better than the other directly comparable constraints, for instance, from the binary pulsar. Finally, the one that I'll talk about most here, because this is the one that actually got the update with this new signal, is these constraints on parameterized distributions relativity, where you actually have some model for the waveform, which has various parameters. You put in these parameters and ask, if you put a deviation, do you actually measure some difference from the parameter directly calibrated to numerical relativity simulations in GR? And the answer is, in this first case, you see that they are consistent. Some of that didn't have a tail, but all consistent with 0. I'll show you this again larger with an update with better calibration. This was done the first cut of the calibration. Now we have the final calibration, and I can show you this later. But also the first that this is the only one that you could have received an update. So the overall star is not high enough to perform the residual test. Just on the merger McDowell is not high enough to perform this merger test. You can perform the method graviton or dispersion test. You don't actually find an improvement, so this has to wait for more data. And of course, you might say, well, what about this other thing that you think is most likely astrophysical? It turns out even if you treat it as astrophysical, it's not high enough SNR to actually help with these types of GR. These really require kind of really top-of-the-line high SNR signals, just because you're looking for small deviations in already very small signals. So here is this first, the updated version of the previous plot. Now just showing in the case where you just weigh one parameter at a time, this is kind of the most sensitive way. So the previous one is showing you causal case where you varied multiple parameters. You might think this is a better thing to do, but it turns out that you kind of get swamped by the correlations in the parameters. It's best to just vary one parameter at a time. This definitely will pick up most deviations in GR, though there's still some tests going on. So here, there's a parameter describing the end spiral, given by this postdoctoral calculation. We definitely know parameters from very difficult perturbative calculations in GR. And here, the parameters directly calibrate from comparisons to numerical sensitivity estimates. These are more phenomenological. So anyway, here you all see that again, it's still in GR. This is from 2013 and 14, the high mass signal. This is from the limit signal, 2015, 12, 26. Here you see it actually nicely centered at the beginning. We think that there was not a realization of noise was quite standard here with the bio getting to these offsets. And here it's with the beautifully present, and you see also you're getting much better constraints really for these order Patinian parameters. Then if you say, we assume that the deviations are pretty much the same, you have a different mass and other different parameters, you combine together to get a joint theory, and then this improves the constraint even more. So this term is actually particularly interesting to look at, that we have a very tight constraint, because this is one thing called backscattering, where you have ways to actually scatter off the background curvature of space-time, and also the lean spin order coupling. This is 1.5 per Patinian term. So then you can also just convert these into other bounds on deviation and some GR of these Patinian equations. So here again, blue is the first signal, second signal, and then this is combined with this. Exactly, in some cases the combination is brought up by a less significant bound where you had mathematical ends power from the first one. In all cases, as we're doing much better to be able to do, say, with the bind also where if you try to follow the same curve, it'd be off. Even here, we're not doing quite as well as bind also it's down and 10 and still below 1 fractional deviation to this policy. So now going on to weights, we can say, well, with one event, we actually don't make a weight estimate, but we have 3 events and about 3 times the data. We have better weight estimates. The answer is yes, but there's still quite a bit of uncertainty to expect these astrophysical things. So there are 2 ways if you have performed weight estimates so far. These may not be all do. And eventually, you have a handful of events. These are kind of things you don't look at. So once you take all the binaries in the universe, you work in 1 or 3 or 1 binary. So you say, well, there are like 3 functions in the universe, one like the high mass system, one like the one that we think is kind of the medium mass system, and one in the low mass system. And you get weight estimates like this, the high mass, medium. So you see that actually the periods go up as you decrease the mass. This is because you only able to see the low mass systems from closer by. So expect if you see one closer by, there are many more further out that you did not see clearly. And you actually just sum and get a little rate. So the other thing we can do is use additional math distribution. So here there are 2 things like a flat lob or a standard power law. And these are kind of picked just to bracket the expected, not exactly expect these to be really statistically realistic. Right? Use some idea of the uncertainty you would have. And then, of course, if you put in the actual then one back, you can be nice in the middle. Also note that this analysis, because it has a model for signals and a model for the noise events, it definitely is able to assign the probability to LVT between 10 and 12 being astrophysical. It's like 87%. For comparison, these other 2 are like 1 minus 10 to the minus 6 as a probability of being astrophysical. So they are absolutely no doubt about it. Here it's like, well, probably it is, but you know, you don't want to put details on it. Okay, so then this is just the thing that you showed you again, which is basically saying that the future is extremely loud, as we would like to say, and they're bright, that we'll see lots of things and listen to them. And also be able to get from 2 to 600 per cubic parsec per year. So this is basically this time volume is the cubic parsec a year. And this is basically how many things you get. This is the old number we got just about the first event. And the second one was on the first 16 days to now 9,240 could be a good deal. So we now expect that biomechanical causes are not going to be anything to write home about. As Rick Feinberg said in the Rex conference for 2026, he looks forward to the day where biomechanical causes by themselves are nothing to hold a press conference about, but only the astrophysicists who get from them. This is, I think, what we all hope for. Obviously, we expect to see lots of interesting things. We hope there's a procession, maybe an intermediate mass spatial black holes or something very large, plus something in the mass gap, but we don't know. But we hope to see lots more of them, and we expect to. So now, kind of the astrophysical implications of all this. So both of these all 3 of these are consistent with quite a wide variety of formation scenarios. So you can either form them by some sort of massive stars that is born as a binary, and it just evolves together. The stars has transfer mass, like a supernova, you form it eventually coalesces. This is kind of the most standard way of forming it, and indeed you can form all these systems. The thing, you need to form them in a region for these heavy ones where there's about half the solar metallicity, there's elements heavier than hydrogen in stars' balance, so you don't lose lots of mass from your stars due to the winds. But this is easy enough done. The LSD looking farther back in the universe is easily below half as low. And then finally, for this one, what is with lower mass? This is more sort of the method that you're hearing about from Ramesh's talk. And it's likely consistent with this case where you have a binary that's tightly locked, and you get kernel homogeneous evolution that does not require hard masses. But besides that, you also form it by one of these binaries where you form it just by a binary that's formed in situ, or a binary where you have dynamical formation, where you have a dense cell region like the classical cluster, or near the classical situ, you have places where you actually exchange probably even tens of times a black hole in and out of a binary, or scatter with other things. And so this is another formation scenario. There's no way of telling apart present, but we hope with more data we'll be able to. So if you have a single formation channel operating, then the fact that we have a lower limit on the rate of 9 per cubic parsec per year, this favors certain theories where you have very high near black hole kicks, where you easily disrupt binaries. But of course, it's more likely that there's more than one formation theory for operating, so you probably cannot put any strong constraints yet. But there's something, again, more data we hope for constraints. Note that still, as we saw with the first one, we have a high enough rate that in a few years of advanced LIGO to be able to see, start seeing the even stochastic background for all the ones that are unresolved, that are far away, they're coalescing, that we don't see the individual sources in the detector, we can actually, stochastic background. And now looking forward to the future, as I think, we hope to actually have in mass and spin population distributions. We have, like, say, the tens to hundreds of sources. And this is kind of a first taste of this in this paper where they said, well, for a very simple thing, because we all have three sources, you have a single power law in mass between 5 and 100 solar masses, kind of the region is searched. And then you can put constraints with power limits of 2 and 5 with a very large error above plus 1.5, 1.6. So to conclude, this is kind of the first taste of the fruits of gravitational wave of astronomy. So I have 2 fermionic coincidences, same with 2, 9, 14, then this layer low mass signal being 12.6, and 1 possible baronic black hole. Total masses span around kind of 30 masses. The final ones are much more massive than anything we've seen previously. We'll be able to say that one component here in 12.6 would definitely spinning, at least 20% maximum. In form phase, that is general relativity. We find no evidence of deviations as yet, which we're continuing looking. And just the geometry 12.6, which is lower mass and has more of the inbound there, has to constrain better the inspire portion of the model. We can constrain the rate of the black hole collision in the universe, and we expect minimal mergers from O2. So this year, so we hope maybe starting in a year, we'll have lots more report on this. And finally, all these signals will provide a model for the information, but these models will become increasingly constrained as we get more resolution. Thank you. At least astrophysically, they definitely are. They're like everywhere.
Okay, questions?
You showed that nice movie of the Inspire.
Yes.
So I could see the entire Inspire, but the so-called ring down. Do you actually see that in the movie?
Yes.
Does it actually
very
oscillate?
Quick, but
Yeah.
I think I have to let it go the entire way. But kind of the last bit when it slowed down, you can actually see, and
What should I look
this
for?
part of this. Oh, but I don't know really things in the movie here, so I'll have to wait for it to go through. If I go here, I can pause it. I'll just let it go, and then so see, you'll note as it hit the peak,
It is breathing.
and then here is where we're actually getting in the window. You can really see it in the change in the horizon.
Very brief.
Yeah, it's extremely brief. So this is why it's very difficult to tease out the data. So they actually tried what you do in 914, and they could see that it's consistent with the window you expect in the final method. It's been used for the other signal, but actually measuring the parameters, not yet. So we hope to actually be able to do this.
Now that there are several cases of different masses and spins,
Yes.
has the evidence of quasi-normal modes become better?
So, I mean, certainly, because we only have one high mass system, we have to wait for some more. Probably, I mean, we're going to have some increased sensitivity in the detector, we hope, next time, so this will help. And we hope that we'll get the several, there's a possibility if you have several, you could probably combine them together to obtain higher evidence for normal modes. But this is still a difficult problem. I mean, really, quasi-normal modes is something you wait for really the space detectors like LISA for. We can still hope with even further generation, probably the third generation gravity detectors like that in telescope. But
so for the previous one, the fact that you could see some of that ring down stage was very important to conclude that it was really a black hole and not some other compact object. But here, since that phase is not, you can, I guess, see a very sharp sort of end to the signal. Is that the main reason to believe that the final object is a black hole and not some compact?
No, I would say it's more that just the consistency of the entire signal with the GR. So I mean, when you're actually looking at, for instance, these parameters, which unfortunately are not very well constrained, but they are consistent. These are the ones describing the merger and ring down. But even here, the signal to noise ratio in the ring down was not that so great. So we are seeing mostly just the end of merger, beginning of ring down. So I think it's mostly the evidence for it being a final black hole. It's just the mass is just as it is in most of astrophysics. I mean, kind of know that the initial objects can't be anything that's too tightly deformable. So you'll see this as a dephasing in the signal. They will be picked up here, but
So if it were neutron stars, you would see some signature in the initial stages as well.
Mm-hmm.
No, but of course there could be some exotic thing.
We haven't done anything so far to rule out possible exotic candidates, but I want to advertise some work that we have started with, led by Nathan and Arunava himself. So the idea is to measure, if there are some exotic object, not a black hole, they get tightly deformed during the inspiral, due to the presence of the companion. And that tidal deformation that we have constraints on the tidal deformability or deformation of the stars, which will have an imprint on the gravitational signal, which you can translate to some of the constraining some parameter space of some of the more exotic models, such as boson stars or gravis stars, etc. So there is some work started in the collaboration to address this question.
See, suppose initially you have established that the initial states are black and there is inspiring. Why would I want to expect anything but a final state that is a black hole? That's what you... That's all. Yes. Yes.